All right, if you would take all your seats, we'll start in about 2 or 3 minutes, and we're looking forward to a wonderful evening together. So 2 minutes, and we'll start.
Can evolution explain math? The Mandelbrot set of numbers reveals a secret code that went undiscovered for thousands of years. While mathematicians can plot this set by hand, today's computers show with great precision that beauty is built into numbers. And when you take a closer look at the Mandelbrot set, you see the pattern goes on without end. This is an example of a fractal, a type of structure that repeats infinitely on smaller and smaller scales. Snowflakes have a fractal quality. Why is this? The laws of nature responsible for snowflake formation are mathematical because they stem from the mind of God. Fractals occur both in math, which is abstract, not made of atoms, and the physical world, which is made of atoms, because they have the same designer. Lightning branches occur in a fractal pattern, and so does broccoli. If the universe was formed by chance, why would nature follow mathematical rules? After all, the number 7 couldn't have evolved from the number 3. Try that argument on your banker sometime. 7 has always been 7, and 3 has always been 3. So when it comes to math, everyone borrows from creation. After thousands of years, we can now plot the Mandelbrot set. Yet the secret code of creation represents just a small window into the infinite mind of God.
All right, we are looking forward to a wonderful time together. This is the second Monday night in our series focusing on origins, unlocking the mysteries of Genesis, how God has laid down the story of creation, and we find increasingly that it is consistent with what science can show for sure. That the Bible is a credible book and it tells the truth about creation. And it's just fascinating to hear things like that when you look into the microcosm under the microscope or you look at the macrocosm through the telescope. We see the glory of God on display. And so this is a series that intends to do just that, to really help us get our minds around the infiniteness of God and His majesty and His glory that's on display in the whole creation. We started on Sunday, a week ago Sunday, looking at why your origins matter, why the question of origins is critical, and how it is a foundational idea for much of the doctrine of the Bible. And so it's important for us as Christians, as believers, to understand and to defend and to seek to explain what God has revealed in the pages of Genesis on the story of creation. And then we looked at the issue of dinosaurs. Many people have questions about dinosaurs. A week ago from tonight, we had some fascinating skeletons of dinosaurs on the stage and in the foyer, and it was fun. We had about 2,000 people last Monday night here to see what does the Bible say about dinosaurs. How do they fit into the story of creation? And many of you, I think we counted them, close to 1,500 people took the guided tours through the dinosaur displays. I mean, that's just amazing. On 3 different opportunities last Monday at 11 a.m. and 1 p.m. and 5:30 in the afternoon. And so it was fun just to see that and to get an expert to help explain how they do, in fact, fit into the story of creation in the Bible. So tonight, we're really excited to have Dr. Lisle back with us and to focus on the issue of astronomy and how astronomy reveals the creation by God. And so I'm not going to waste any more time. You guys came here not to hear me, so we're going to welcome Dr. Lisle to the stage right now. Dr. Lisle.
Oh, good evening, folks. It's my pleasure to be with you this evening and talk about how astronomy reveals creation. And in particular, I'm going to focus in on the solar system, just one aspect of many things that the Lord created in the universe. And we'll see how the solar system reveals biblical creation. It really does. So we've already seen how origins really is very important because Christian doctrines go back to Genesis. All of them, directly or indirectly, are related back to Genesis. And you can't really defend Christian doctrines apart from that foundational book of the Bible. If the history of the Bible is not true, why would you trust the other areas? Why would you trust God's message of salvation, for that matter? And we've seen that the Bible has been attacked largely in the area of Genesis. That's where folks say, well, we know from science that millions of years, of evolution, that's the way that life came about. And, the universe exploded into existence 13.8 billion years ago in a Big Bang and so on. And, in 2 of the areas that people really kind of focus on, that evolutionists sometimes use as icons of evolution, would be dinosaurs, and another one is astronomy. And so we want to hit those extra hard. Dinosaurs do fit in with the biblical time scale. If you joined us last week, you know that. And I want to show you that astronomy fits in with the biblical time scale. What we're going to see as we explore each of these worlds of creation is that each one of them is something that it brings glory to God, really. It's something that reveals His creative diversity. It's just fascinating. It's interesting. It's something that is consistent with the biblical time scale of thousands of years. And it's something that defies secular explanation. And we're going to find that's true as we explore these worlds of creation. The thing that's interesting to me is the way that God has sort of hidden these little secrets in His universe. It reminds me a little bit of there's an activity that some folks like to do around Easter time. They hide Easter eggs for their kids to find, and youngsters enjoy finding these beautifully colored, in many cases, eggs, and it's sort of fun to find something that's been hidden, and we get enjoyment out of that, and that's fine. But God does that in the universe. He's hidden these little Easter eggs for us to find, and when you discover them, they're beautiful and they're interesting. And they say something about the mind of God. And so that's really what I want to focus in on this evening. I just hope that you just enjoy the beauty and the majesty that the Lord has poured into his solar system. And of course, our solar system we now know is one of many. There's other solar systems out there, stellar systems, I should say. But in any case, I'm going to use some software here to show you how the solar system looks. That's what it would look like from above. That's the inner solar system. And so you've got the inner planets there, Mercury, Venus, Earth, and Mars. Those are the terrestrial planets, meaning they're Earth-like in the sense that they're solid bodies, and they orbit relatively close to the sun. Mercury and Venus closer than Earth, Mars a little further away. The outer planets orbit quite a bit further away, and that's not always something that we appreciate, but when you zoom out a bit, you can see they're much further away from the sun. And they're non-terrestrial. They tend to be gas giant planets, so balls of gas held together by their own gravity. We may take it for granted. We live in an age of scientific enlightenment, and you say, of course, that's the solar system. We understand the Earth is spherical and it orbits the sun. We get that, but I hope you appreciate the insight that went into discovering this. It's quite wonderful. I mean, the Lord has put us on this little sphere. It seems big, but it's small compared to the rest of the cosmos. And it's spinning and it's moving around the sun. And it took some very clever minds to figure out that we're on one of these planets orbiting the sun, and there are other planets, and they orbit the sun. And one of the minds that really figured out kind of how this works is Johannes Kepler. He was a creation scientist, and he was the one that discovered that planets orbit the sun not in perfect circles, as some had thought before, but in ellipses, which is kind of a squashed circle. Now, they're only slightly squashed, but they are a little bit. And you can see that with Mercury's orbit here, for example. You can see Mercury orbit is farther away from the sun here than it is there. It's a little bit kind of offset. It's a little bit squashed and offset. And it was Kepler that discovered that. And you say, well, yeah, I mean, that's not so impressive. I can see that. But he didn't have a computer that could display it like this. It's remarkable that he was able to discover that, because you need to understand we're on one of those little specks. And when you watch the other ones move, it's complicated because we're moving too. And you don't know quite how, you don't know the distance to them. You can't see that because we're on one of them. And if you look at the solar system, they're all pretty much in the same plane, which means you don't even know where they are. As far as you're concerned, the planets seem to go back and forth in the night sky, and they sometimes they'll stop in reverse direction and go the other way for a little while and then switch back. And they were able to figure out eventually that the planets, in fact, are orbiting the sun, and that's why they move the way that they do. And it's really pretty ingenious. In a lot of textbooks, you'll see the solar system displayed from a perspective view like that, where it's kind of not quite edge on. And sometimes people will think that the orbits are very squashed because they think they're looking at an overhead view, but it isn't. If we look at it from above, the orbits are pretty close to a circle, but we know mathematically they're just a little bit squashed. So planets orbit the sun in elliptical paths with the sun at one focus of the ellipse. An ellipse is defined by 2 points. It's the sun, all points that are equidistant from 2 points. And the sun is at one of those. The other one is empty. And so that's what they look like. That's Kepler's first law of planetary motion. Kepler was a very devout Christian, and he believed that doing astronomy was like thinking God's thoughts after him. And that's one of his quotes that I really enjoy. Yeah, a very humble man, too, and a very brilliant scholar. Kepler also discovered the way that the planets orbit. Planets orbit in such a way that the ones that are closer to the sun orbit quicker, the ones that are farther away from the sun orbit slower. And within an orbit, since the orbit's elliptical, Mercury is sometimes a little closer to the sun, sometimes further away. And when it's closer to the sun, it speeds up a little bit. And Kepler found the exact mathematical expression that expresses that. He found that planets sweep equal areas in equal times. That's Kepler's second law. And then finally, he was able to discover the relationship between the distance that a planet is from the sun and its orbital period. And so if you know one or the other, you can compute the other one from it. If you know a planet's distance from the sun, you can compute its orbital period, how long it takes to orbit the sun. And that's expressed in Kepler's third law. And Kepler's third law really becomes obvious when we zoom out to these outer planets. You can see that they're just barely moving. They really take quite a long time to orbit the sun. And so we really have to speed things up here to get those outer planets to move. Let me speed up time a bit. Okay? And we'll go to the outer solar system. They're really moving, right? Outer planets just barely moving. Barely moving. So we'll speed up time even more, 10 times faster. And the inner solar system's really whipping around there, but you can see Jupiter. Finally, we got it to move. Saturn takes about 31 years to orbit the sun once. And so it's just kind of amazing how long they take. Of course, Uranus is even longer. Neptune, by the way, in 2011, Neptune completed its first orbit since it was discovered. So it's just amazing to think of the long time periods that are involved here. It really challenges our minds. And Pluto hasn't even made half an orbit since it was discovered. So it's still quite a ways out there. Okay. Well, it was another creation scientist, Isaac Newton, who came along and figured out why it is that planets orbit the way that they do. And he realized that it was the sun's gravity that was causing the planets to orbit like that. You see, things tend to go in a straight line, but gravity bends that line into an ellipse. And that's why planets orbit the way that they do, and it's why moons orbit planets the way that they do. Moons orbit planets also in elliptical paths with the planet at one focus of the ellipse, and again, the math follows there. By the way, this is the way the planets are right now as I'm giving this presentation, and so that's their current configuration. And it's what we're going to do is go to each of these worlds and see how they're just wonderful and interesting and beautiful, and how they reveal God's glory. And we're going to start with the sun, actually, because the sun is most of the solar system. By mass, it's 99.98% of the solar system, so we can't leave the sun out. And this is something that I spent a lot of time studying in grad school. I actually studied the surface of the sun and how it moves. And it is constantly in motion. The sun is a ball of hydrogen gas held together by its own gravity. And in the core, the pressure and temperature are so high that hydrogen is fused into helium, and that releases energy. It's kind of a stable hydrogen bomb, really. And that's a very efficient source of power, but it's perfectly safe because the outer layers protect us from any dangerous radiation from the interior, and Earth's magnetic field takes care of most of the rest. So it's at the right distance and so on for us to receive the right amount of heat and light. You can see that the sun it does have features on its surface. It has these small things that you see moving there. Those are called supergranules, and they're constantly moving around. I've got sped up. They're not quite that fast, but they're constantly moving around like that. And each one of those is about the size of the Earth. If I were to zoom in even more, you could see smaller structures called granules. They're smaller versions of supergranules, and they're only about the size of Texas. Okay, so there you go. And you can see some dark features on the sun as well, sunspots, and they do occur on the sun. And those are actually cooler regions on the sun. The sun's surface temperature is about 6,000 degrees Celsius. And so sunspots are where the temperature is dropped to a chilly 4,000 degrees Celsius. And so, that's the sun there. And of course, I'm sure you'll all want to read my doctoral dissertation later, so I won't spend a lot of time on that. You really wouldn't. Okay. And of course, the sun's what keeps all the planets orbiting the way that they do. First planet out from the sun, Mercury, which is 3 times closer to the sun than Earth is. And it's 3 times smaller than the Earth is, so it's kind of nice. It makes that easy to remember. And Mercury is, wow, it's kind of like the moon. It's a very desolate world. There's no atmosphere on Mercury, and for that reason, anything that comes close to Mercury just hits the surface. There's no atmosphere to protect it from meteoroid strikes, and so it's just covered with craters. And we think maybe God may have used some process when he created these worlds on day 4, because all these planets are made on day 4 except Earth, which is day 1. And so God may have used some process to bring the material together there. In any case, it's a really interesting little planet. And one of the things that is interesting about Mercury is it has a magnetic field. And whenever you find magnetic fields, that's an indication of youth. It's an indication that this planet cannot be anywhere near billions of years old, because magnetic fields naturally decay with time. You can make a magnet by taking a coil of wire and touching it to the ends of the battery, and it'll become magnetic. But eventually the battery runs down. Electrical current encounters resistance, it runs down, and we've been able to measure that with Mercury's magnetic field. There's evidence that it is dropping. We've been able to measure it in the 1970s when we sent a spacecraft past Mercury, and then we did that again just a few years ago with the Messenger spacecraft. And there's evidence that the magnetic field, not only is it there, it's dropping a little bit, just as we'd expect in biblical creation. And so it's not a problem for a few thousand years. I should mention, too, that all the images that you're going to see tonight, these are real. These are what you would see if you were there. I feel very blessed to live in the time that we live in, because you see, as of last year, as of July 2015, we have visited every large world in our solar system with spacecraft, and we have high-resolution images of their surface. And so it's just a privilege that we live in a time where, I mean, for our ancestors, Mercury was that little point in the light sky that moved faster than the other ones. That's it, really. And now we have these wonderful images of its surface, and we know something about its composition, we know what it looks like, we know how it behaves, and so on. The other thing you might notice is Mercury rotates very slowly. Now, I've got time sped up here, but it actually takes something like 58 days, I believe, to rotate once on its axis. So it's a very slow rotator, but it's the fastest orbit, right? Because it takes only 88 days to orbit the sun once. So that's kind of interesting. The day side of Mercury, because there's no atmosphere and because it rotates slowly, it's just getting baked by the sun. And so the surface temperature can get up to 800 degrees Fahrenheit. Very, very warm on Mercury. And the night side, because there's no atmosphere to distribute the heat, and the night side just radiates that heat into space for a long period of time, it cools off to like negative 200. So it's a planet of extremes. But of course, there would be one location right on the boundary there, right where sunrise is happening, where the temperature would be kind of okay, right? That would have to be the case. So if you're going to crash land on Mercury, you want to land right about there, just before sunrise. And the really interesting thing is, because Mercury rotates very slowly, if you crash landed right about there, now it's just about to be sunrise, and you don't want to see sunrise because the temperature is going to go up to 800 degrees. You don't want that. So you start running west, right? And Mercury rotates slow enough, you could actually outrun sunrise. As long as you keep running west, you're going to be okay. You're going to survive. So now you know what to do if you ever crash land on Mercury. You're welcome. The next planet out is Venus, and it's been called Earth's sister planet because it's just about the same size as the Earth. It's just ever so slightly smaller. And that's about where the similarity ends. Venus is very different from Earth in almost all other respects. For one thing, it rotates backwards. That's kind of interesting. And that is absolutely contrary to what you'd expect from the secular idea of how planets form. You see, in the secular view, the idea is the entire solar system formed from a collapsing cloud that eventually became a disk, and everything ought to really be spinning in the same direction because due to conservation of angular momentum. And of course, all the planets orbit in the same direction, and most of them rotate the same way, but not Venus. It's just exactly the opposite of what you'd expect in the secular view. And I just think that's wonderful, and I love that the Lord does that, maybe just to confuse the secularists. Maybe for no other reason than that. Or maybe just to show that he's creative and diverse. In any case, that's very interesting. Venus is permanently enshrouded in clouds, and so you can never see the surface. And for that reason, in the past, people thought, well, not all people, but some people thought, well, maybe Venus might have life on its surface, right? And that was especially prominent among secular astronomers who think that life on Earth is just the result of chemistry that happens over time. Life evolves, right, when the chemistry is right. Maybe Venus, a little closer to the sun, could be a tropical paradise world, right, a little bit closer, and it might have all kinds of exotic plants and animals, and they were free to speculate because, again, you can never see the surface. It's always nice when you can speculate unfettered by inconvenient data. In any case, but that was all before they discovered the surface temperature is 900 degrees Fahrenheit. Yeah, so you're not going to find plants and animals on Venus. It's hot enough to melt lead. So, and it's actually hotter than Mercury, and that's because that atmosphere is incredibly thick, much, much thicker than Earth's atmosphere, and it traps in the heat. It's a greenhouse effect. And, some of the climate change alarmists are saying, well, that might happen on Earth. Well, it can't happen on Earth because our atmosphere isn't nearly as thick as Venus. It won't support that. But it does happen on Venus, and so you would not want to live on Venus, not with the surface temperature of 900 degrees Fahrenheit. And there's no water anywhere on Venus. So there's no humidity, so it'd be a dry heat for whatever that's worth. But yeah. And those clouds that you see there are made up of sulfuric acid type compounds. So there's just lots of wonderful ways to die on Venus. It is not a place you want to vacation, not at all. We've sent spacecraft to Venus, and they've actually gone into orbit and mapped the surface using radar. Radar can penetrate clouds. And so we now know the surface of Venus looks like this. That's what the surface looks like. Let me spin it around here a little bit so you can see it. Very desolate world, very slow rotator. Not only does it rotate backwards, it rotates backwards very, very slowly. And so the sun would rise in the west on Venus and set in the east, but you'd never see it because, again, it's permanently cloudy, permanently overcast on Venus. And so, again, it just defies secular explanation as to why it rotates the way that it does. Very interesting planet. By the way, the atmosphere on Venus is so thick that it bends light significantly. This happens a little bit on Earth. When you see the last little glimmer of sunset, the sun's already set, but the Earth's atmosphere bends the light up just a little bit, so you can see the sun a little bit longer than you would be able to if the Earth had no atmosphere. With Venus, the entire surface has been up above its own horizon. It's very strange in terms of the way it appears. So it would look like you're standing in a bowl. Instead of going down, it seems to go up a little bit. Very interesting. And so in principle, if you were standing on the North Pole of Venus and you had a telescope, you could see your friend standing on the equator because of the entire surface, you see, gets bent up. You could see yourself, theoretically, if you look long enough, because the light would go all the way around. It's really interesting. So it's just interesting, these situations that don't really occur on Earth, and to see them in space. Now, the third planet out, I have to admit, is my very favorite. This is Earth. All my friends live there, and so I like it quite a bit. And it is a unique planet. It's terrestrial, like Mercury and Venus. It's solid planet, but it has a liquid surface. Most of it, 71% of the Earth's surface, is covered with liquid water. And that's very convenient and very essential for life. Life requires water, and so and it needs to be in that liquid state. By the way, water is a very common molecule in the universe. Very, very common. But it's almost always in vapor state or frozen. It's in ice. And it takes the right temperature range and the right pressure conditions to have it in a liquid state. And so we're very blessed and very privileged to have a planet that has just abundance of what you'd need to have life. This is, of course, what it looks like today. Now, the Earth did not always look like that. We believe that before the flood, the continents were different and looked something like that. Now, this is a work in progress. We're going to update this as we get new information. But one of our staff geologists is actually measuring megasequences, and that allows him to reconstruct what the world might have looked like before the flood. Very interesting. So we think that during the flood year, there was catastrophic plate tectonics that pushed that original supercontinent apart and then reassembled it and then pushed it apart again into our current continents. So it's interesting to see how this world has changed with time. Earth has a magnetic field, and that's something that naturally decays. And with Earth's magnetic field, of course, we know a lot about it because we happen to live here, and so we've been able to take really good measurements of the Earth's magnetic field almost for 200 years. We've had measurements of it. And it is decaying. It's decaying exponentially, which is what we'd expect, given that electrical current causes magnetic fields. And if you run the movie backwards, you find that Earth's magnetic field would have been 20 times stronger at creation, which would be nice. It would give us increased protection from cosmic rays and so on. But because it's an exponential decay, you can't run it back very, very far. If you run the Earth's magnetic field back as much as 60,000 years, it would be stronger than a neutron star, which is enough to basically rip your atoms apart. So you see, the Earth can't be anywhere near even a million years old, let alone billions. The magnetic field is inconsistent with the secular view. And there's a lot of stuff like that on Earth. That's just one example of that. The Earth has one moon, one large natural moon anyway, and we just call it moon because we're not very creative. That's what it looks like. You've seen the moon. It goes through phases, and that just has to do with where the sun is relative to the moon. So there's new moon. In new moon, the sun and the moon are kind of in the same spot in the sky, and so the sun is illuminating the other side, and we're seeing the night side of the moon when it's in a new phase, and so you don't really see it, except during a total eclipse, which are pretty rare. And then when the sun is just a little bit on the right side there, that's a waxing crescent phase. Waxing means it's getting bigger, and crescent because it is one. And then first quarter, when it's illuminated right down the middle, first quarter, because it's 1/4 of the way through its cycle. Go a little bit past that, we have a waxing gibbous. Gibbous means fat, so the moon's getting fat, and waxing because it's getting bigger. And then we go to full moon. And so if you think about it, the sun would have to be opposite the moon in the sky, right, when the moon is full. And so that tells you that you can actually, it's very easy to compute when the full moon will rise, because it's going to rise when the sun sets. They're opposite. And it'll be out all night, and it'll set when the sun rises. And you can do that with other phases too. It's just a little bit more, you have to think through, okay, how far ahead of the sun is the moon when it's in that phase. And here we have a waning gibbous, and then third quarter, which is a nice phase. The moon is beautiful when it's in one of these quarter phases, either first or third quarter, because you can see the shadows of the craters. The sun illuminates them very well. When it's full, the sun is shining down into the craters and they don't cast a shadow. And so the moon looks very flat. But when it's in one of these quarter phases or even crescent, it looks very three-dimensional. Your brain is able to figure out that it's a sphere. It's pretty remarkable. So that's the moon. Now the moon is rotating. A lot of people think that it doesn't rotate because we always see the same side, right? That sort of man in the moon feature that you see there. And that is the side of the moon that we always see. But it's because it's rotating that we see the same side. If we were to watch the moon from a distant star, we would find that it is rotating. It just keeps the same face pointed toward the Earth. So as it revolves around the Earth, it keeps its same face pointed at the Earth, and eventually the Earth will appear in the background there. There it is. And if I lock it on the moon here, so if you were living on the moon, the stars would rise and set because you're on a rotating world, but the Earth would remain in about the same spot in the sky. And you could sit there and just watch it spin over. This is time lapse, of course, but I think that'd be remarkable. And I must admit, I've always been just a little bit jealous of the astronauts who got to walk on the surface of the moon, because they got to see that. And what a spectacular thing to stand on the moon and look up and see this little jewel there and realize how delicate it is. And it's only by God's power that we're kept safe, All your friends, all the billions of people, all on that little blue sphere. Really amazing. There have been very few people that have gotten to experience that view. But it'd be quite spectacular, I think. Okay, back home, back to Earth. We do have a number of artificial moons orbiting the Earth, including the International Space Station. You can think of that as an artificial, man-made moon. It orbits the Earth, and it looks something like that. And I think that would be fun to experience too. Of course, a lot more people have gotten to experience that, but still relatively few. A friend of mine actually is on there right now, Jeff Williams. He's the current commander of the International Space Station, although he's coming back maybe this week. In any case, that would be a spectacular view. I would love to. Can you imagine looking out your window and seeing that? That would be amazing. And wow. What a beautiful world we live on. And what a privilege that we live in a time where we know what it looks like from above. And it's just absolutely beautiful from above. Really stunning. Of course, there's several hundred. There are lots of satellites orbiting up there, but the International Space Station is really it's the largest one. And you can see it in the night sky. If you know where to look, you can go to different websites, and they'll tell you when to look, and you can watch it go overhead, and it's fun to say. And you can wave to Jeff up there. Okay, well, let's go out. So that's Earth, our favorite, my favorite anyway. Best restaurants on Earth. The next one out is Mars. And although Venus has been called Earth's sister planet, Mars really is probably the most Earth-like planet in terms of its basic features. Let's do that there. So Mars looks something like that. It's the red planet. It's made up of lots of iron compounds that have oxidized. So it's kind of like a rust, really. And that's, rust has that red color to it because of the iron. And so Mars is very similar to that for that reason. And it does look red. And in fact, you can see it this time of year. If you go out and look in the southwestern sky after sunset, that really bright reddish orange star, that's Mars. And there's another orange one just below it, that's Antares, whose name means rivals Mars, because it looks very similar to Mars. People confuse them, but Mars is the brighter one, at least this time of year. So there it is. It's got a lot of features that are similar to the Earth, but some differences too. You can see it's got some craters on it, so it's kind of in between the moon and the Earth. It's got some craters, but it's got some Earth features too. It has dried riverbeds, so we think that Mars had liquid water in the past, although it apparently doesn't today. It's got valleys and canyons. In fact, you can see this large canyon here. This is the Valles Marineris Canyon. It's like the Grand Canyon, but much bigger. It would be as long as the United States, actually. So it's an enormous canyon, a tectonic fissure. And then we have mountains. You can see those mountains there. And the one up at the top there, that's Olympus Mons. That's the largest known volcano. And those are all volcanic mountains. They're all thought to be extinct, but they may not be. We creationists think that Mars might still have some internal energy, and we might see those erupt at some point in the next 100 years or so. So if it happens, you heard it here first. That's our prediction. We think it's at least possible. Olympus Mons, the largest of those volcanoes, is 3 times taller than Everest, and the base of it would cover the entire state of Iowa. So that is one big volcano. But other than that, Mars tends to be relatively flat. It does have some hills and features on it, but it's kind of the Kansas of planets. It really is relatively flat. You can see some of the features with a small telescope. That dark feature is Syrtis Major, and the valley below it is Hellas, which often fills in with fog and kind of looks very bright, a very bright color. And I've seen that in a small telescope. It's fun to look at. Mars has polar ice caps, a bit like the Earth does. But Mars's caps are made mostly of carbon dioxide, dry ice, a little bit of water ice in there as well. But it does have those. And they shrink and they grow with the seasons, just like Earth does. And Mars does have seasons, just like the Earth, because it's tilted. So there's the northern polar ice cap, for example, and that grows in the winter and shrinks in the summer. Mars has a 24-hour and 37-minute day, which I think is kind of neat, because that means it'd be kind of like Earth, but you could sleep in an extra half hour every morning, and it would never catch up with you. I think that's neat. I'm not a morning person, as you can probably tell. But anyway, so yeah, and it has so some similarities to Earth, but some differences too. It doesn't have the global magnetic field that Earth has, because Mars is a smaller planet, and it can't seem to retain that magnetism. It does have remnant magnetism, which you can think of like little bits of randomly oriented magnetic field in its crust, and that indicates that it was created with a magnetic field, but in 6,000 years it's already run down. So so small stuff like that that's not very conductive, it can't even maintain a magnetic field that long. But even the remnant magnetism would be gone if it were billions of years old. So it's still an indication of Mars's youth. But despite all its similarities to Earth, it's got a lot of differences. It's about half the size, so the gravity is going to be weaker. The atmosphere is very thin in carbon dioxide, so you could not breathe on Mars, nor grow potatoes, by the way. You know what I'm referring to. Okay. It doesn't have liquid water on its surface today, may have in the past. And so it's really not designed for life. It's too cold. It's much colder than the Earth is, so it's not designed for life. It does have moons, 2 moons, and they're tiny. They're Phobos and Deimos. Let's zoom out here to Deimos, the outermost of the 2. You can see these in a modest backyard telescope, but you have to really know what you're doing because they're faint. And the first thing you might notice about Deimos, let me speed up time here a little bit, it's not quite round. It's kind of got that potato shape to it, and that's pretty common for small moons. It's only about 10 miles across, and so moons that are that small are not massive enough to pull their shape into a sphere, and so it just kind of has that they can sort of, it's like a big boulder in space, basically, that happens to be orbiting Mars. And so Deimos is the slightly smaller of those 2 moons. The inner one is Phobos. The names mean fear and terror, and of course, Mars is named after the god of war, and fear and terror accompany war, so that sort of makes sense. So there's Phobos, and you could imagine being on this little moon, about 10 miles across, so that you could walk around that. That'd be a good hike for the day, right? And imagine looking up in your sky and seeing Mars like that. See, Phobos orbits really close to Mars, and so it would be a spectacular view. The gravity on Phobos is so weak, you could actually pick up a rock and throw it into orbit. And you better duck, because it's going to come up and hit you in the back of the head. So again, it's interesting to see these situations that just can't occur really on Earth. So Mars, a lovely planet. That would be the one that if you were going to try and put a colony, bring a little bit of Earth with you, a little bit of water and air with you, that would be the one to do it on, because that's the one that will kill you the slowest. All right. Now, these planets we've looked at so far, these are the terrestrial planets. They're all like Earth in the sense that they're rocky and solid. The outer planets are quite different, and they're all bigger than Earth: Jupiter, Saturn, Uranus, and Neptune. And you can see there's a gap between Mars and Jupiter. Jupiter's much further out. It's 5 times farther from the sun than Earth is, and that's going to be the next world that we look at. And Jupiter's a lot of fun. It's a wonderful object to look at in a small telescope, a lot of fun. It is a ball of gas, held together by its own gravity. Yes, gas has gravity. Everything has gravity. Everything that has mass has gravity. And you get enough of it, it'll hold itself together. It's about 10 Earths across, to give you a feel for it. So it's a big, big planet. And it rotates relatively quickly. It takes 10 hours for it to rotate once. So it's a fast spinner, which is fun because when you're looking at it with a small telescope, sometimes you'll see a storm develop on its surface, or the Great Red Spot, for example, right here. And you can watch it over the course of the night. You can watch the red spot move from one side to the other. You can watch it rotating. It's kind of neat. The red spot here, it's about 2 Earths across. It's basically a giant hurricane that has existed on Jupiter for at least 300 years, since we've had telescopes that have been able to see it in that depth. It's been there. And now hurricanes on the Earth, they move over land and they lose their power source, right? And so they die away. But on Jupiter, there's no land. It's a ball of gas. And so once that hurricane gets going, it just continues to go, apparently forever. Kind of interesting. And we don't really understand all the mechanics of how fluids work on planets like that. We have some idea, but we don't know if the red spot will continue to exist forever. It might have been there since creation, for all we know. It is shrinking. It was a little bigger a few decades ago than it is now, but whether that's a cycle and it will come back, or maybe it'll go away and Jupiter won't have a red spot anymore, we don't really know. It's fun to see these different physics experiments that the Lord has set up for us on these other planets. You might notice the very prominent features on Jupiter are these large belts and zones. Belts are dark and zones are light, and they encircle Jupiter, and they're just clouds, basically. Jupiter is made of a number of different compounds. It's mostly hydrogen and helium, but trace elements, things like methane and ammonia, there's a lot of that in there. And it's the ammonia, I believe, that gives the orange color, maybe the methane, I forget. Anyway, and the white ones are a little higher up, and so they're blocking the view of the clouds below. And it's kind of like jet streams on the Earth. You know, the Earth has jet streams. It's got, that flow in different directions depending on the latitude. And Jupiter has a lot more of them because it's a bigger planet. But it's just jet streams, that's all they are. And the red spot's sandwiched in between 2 of them, just below the southern equatorial belt and the southern the zone below that. And of course, Jupiter bears all indication of being nowhere near billions of years old because it has a very strong magnetic field, the strongest of any planet. In fact, it would be too strong for life even today. We now have a spacecraft orbiting Jupiter, the Juno spacecraft, and they had to build it very special to protect the circuitry just from Jupiter's magnetic field. So it's pretty remarkable. And we know magnetic fields do not last billions of years. They naturally decay with time. And so when you find a magnetic field like that, it's an evidence of youth. Jupiter also gives off twice as much energy as it receives from the sun. It takes in 1 unit, gives away 2. It takes in 1 unit, gives away 2. And it can't do that anywhere near billions of years, or it would have exhausted its heat long ago. It still has that internal energy. Jupiter has a number of moons, and let's take a look at some of those. It actually has over 60 moons, but only 4 of them are big. And you can see at least 3 of them here. Io, Europa, and Ganymede are 3 of the big ones, and then Callisto is off the screen at the moment. But these were discovered by Galileo in 1610. Galileo was not the first person to use a telescope, but he was one of the first, and he was the first to point it up and document what he saw. And in January of 1610, Galileo pointed his telescope at Jupiter. And of course, we see Jupiter from sort of an edge-on perspective. And when it's edge-on, the moons just kind of go back and forth, right? They look like they're in a straight line relative to Jupiter. With the computer, we have the advantage of being able to see it in a perspective view. But Galileo saw these 3 little starlets in a perfectly straight line with Jupiter. And he thought, well, that's kind of interesting. He thought they were background stars initially. And then the next night when he goes out to look, he sees they seem to have moved. Well, how can that be? And of course, he knew that Jupiter was moving and maybe it got ahead of the stars. Well, no, because Jupiter's supposed to be going that way. And so how did the stars get ahead of it? He couldn't figure it out. And then after a few more nights, he sees them swap positions and he realizes, oh, these are little worlds that orbit Jupiter. Nobody thought of that. Nobody thought that other planets could have moons, right? There was the Earth, and we knew about the moon. And there was some debate at that time as to whether the Earth orbited the sun, or maybe everything orbited the Earth, including the sun. That was another competing hypothesis at the time. And Galileo had very good evidence that not everything orbits the Earth because he could see these moons orbiting Jupiter. Io, Europa, Ganymede, Callisto. There's Callisto out there in the perimeter. And of course, he would have, I would love to bring Galileo forward in time and show him the surface of these moons. We've visited them now with spacecraft, and so we know what they look like up close, and they're spectacular. Let's go to Io first of all. Io is my very favorite moon because it looks like a pizza. Isn't that neat? And those features that you're seeing there, that's Jupiter, shadow falling on it there. The features that you see there are volcanoes. Io is the most volcanically active world in the solar system. When Voyager 2 flew past Io, it spotted 9 volcanoes going off simultaneously. It is a very active little moon. And there's a number of reasons for that. But one of them could be just because it's young. It hasn't had enough time to dissipate all its heat, but it may get a little gravitational tugging from Jupiter. I want to freeze that for a moment because you'll notice there's 2 spots that have formed on Jupiter there. That's the shadow of 2 moons. And you can see that in a small telescope. And it's a lot of fun to watch that and to watch how the moons orbit around Jupiter. It takes a hour or 2 for the moon to cross in front of it, and the shadow moves from one side to the other. You can see that in a small telescope. A lot of fun. Anyway, Io is a very fun moon with volcanoes constantly going off along its surface. Nothing looks like Io. It's totally unique. It's about the same size as Earth's moon, just for comparison. But the surface is just crazy. And you even notice the colors. If you've ever been to like Yellowstone National Park and you've seen if you've been to the geysers area, it has kind of those colors because of the sulfur compounds. That's basically the same kind of chemistry that's going on this little moon. So that's Io. Now the next one out is Europa. Europa is just a little bit smaller than Io. And again, just a crazy surface, not what you'd expect for a moon, especially if you're a secularist and you think these things just all sort of formed by chance. Europa is an icy world. That's why it has that light color made of different ices. And it's got these large streaks across the surface, like a big cosmic cat just came and swiped it like that. And I have no idea what causes that, so don't ask me. But it is interesting. It's very interesting. It's like and there appear to be sort of icebergs in a frozen ocean too. So maybe part of the surface was liquid at some point, but today it's too cold, and so it's all frozen over. The next one out is Ganymede, which is the largest moon in the solar system. Ganymede is actually larger than the planet Mercury, but because it orbits Jupiter instead of the sun directly, it's a moon rather than a planet. If you could detach it from Jupiter and have it orbit the sun directly, it would certainly be classified as a planet. And so we'll speed up time there. You can see it's a lovely moon, and it's got kind of tritone color there, light brown, dark brown, and white, very pretty. It kind of makes me feel like we got ripped off on our moon because it's just grayscale, but and then Callisto is the next one out, just a little bit smaller than Ganymede. And so again, isn't it amazing? And this isn't fake. These are actual texture maps that we've derived from spacecraft that have flown past these worlds. That's what they look like. That's what it would look like if you were there. And just amazing that we live in an age where we can do that sort of thing. Very remarkable. Okay, back to the planet. Now, Jupiter's inner moons, you can see they all orbit in the same plane in nearly perfect circles, all in the same direction. And that's a design feature because you see there's not a lot of space available there. And some of those moons are big, right? The big 4, Io, Europa, Ganymede, and Callisto. And so there's not a lot of space available. There has to be some organization so that moons don't collide, or if a big moon got really close to another big moon, they would gravitationally interact and they could kick each other out of the system potentially, or one of them could get kicked out. And so that's a design feature that inner moons all orbit in the same plane in the same direction. But outer moons do what they want. Yeah. And you can see they're not even in the same plane. If I rotate it edge on here, you can see it's just crazy. And it looks like a big mess. Now, each one of those is a perfectly well-defined elliptical orbit. Perfectly well-defined. It's just they're all different. And so it looks like this crazy mess when you see that. And of course, I could speed up time. And again, the moons that orbit close, they orbit fastest. The moons that are farther away orbit slower. I really have to speed up time to get those outer moons to move. There we go. And you can see that a lot of them orbit Jupiter backwards. Isn't that interesting? And so they're just the opposite direction of some of the other ones. And again, that's fine because it may not look like it may look crowded, but there's a lot of space available out there. And these moons are all tiny. Some of them are just a few miles across. And so there's a lot of space available. They don't need to be organized in any way. The chances of collision are negligible. So again, that's a very common feature we're going to find, that inner moons have that tremendous organization and outer moons kind of do what they want. Very common feature in the solar system. So that's the Jupiter system. Next out we have Saturn, which aside from Earth, Saturn's my favorite because of that lovely ring system. And the planet Saturn is actually pretty similar to Jupiter. It's a ball of gas held together by its own gravity, and it has belts and zones, but they're not as pronounced as Jupiter. You can see the northern equatorial belt there, very faint. The southern one is almost non-existent. And but of course that ring system just takes the cake, doesn't it? And that's trillions of tiny little moons that orbit around Saturn's equator, and so many of them they just seem to form kind of a sheet. And this was very perplexing when Saturn was first seen in a telescope, because they couldn't see it in detail like that. All they could see is that there was something to the left and right of Saturn, and Galileo could see it. He didn't know what it was. That was the central problem in astronomy in the 1600s, is what is the nature of these things next to Saturn? And then finally, once the telescopes got a little more powerful, somebody realized, oh, a disk would do that. If it was a tilted disk, it would do that. And there was the debate about what is it made of, and they finally figured it out. They finally realized it was trillions of tiny little moonlets. And now we've been there. We've sent spacecraft past Saturn. We've got one orbiting, the Cassini spacecraft, I believe, is still orbiting Saturn. And in any case, it took some wonderful images of Saturn and of its moons. And Saturn's a lot of fun to watch. Sometimes storms will develop on the planet, and you can see them in a small telescope. You'll have these white or black storms that'll develop, and you can watch them move across. It's really stunning to look at. You might notice the rings come in sort of sets. There's three main rings. There's the outer A ring, and then the B, and then the C is the innermost, and C is the faintest. And the A and B are just obvious when you look at it in a telescope, and sometimes you can see the C. But there's a gap, there's a division in between rings A and B, and that's the Cassini division. And we think that's caused by a moon, the moon Mimas, which I'll show you here in a minute. The idea here is Mimas actually orbits outside Saturn's rings, and so how could it cause that gap there? Well, the way it works is if there was a particle orbiting inside that gap, it turns out that the math is such it would orbit at twice the speed of Mimas, twice the angular speed. So every time it makes 2 orbits, Mimas would make 1, which means every 2 orbits, it would be in the same place at the same time, and Mimas's gravity would pull on it repeatedly every 2 orbits until it finally kicks it out into a higher orbit, you see. And so Mimas kind of acts like a vacuum cleaner that sucks out particles out of that little division. So let's see what Mimas looks like. Let's zoom in on it here. I really do like Mimas. Now it looks a little bit more like a moon you might expect, and it's got this large crater right there. And when the light hits it just right, it absolutely looks like the Death Star from the Star Wars movies. Absolutely. And it really is neat to see it. And of course, the angle's not quite right here, but you'll see pictures of it, and you're inclined to say, that's no moon, it's a space station. But it really is a moon. It really is a moon. It orbits just a little bit outside the plane of the rings, too, which is unusual. But that's kind of neat, because if you lived on Mimas, then you could actually see the rings of Saturn. Other moons, not so much. So let's take a look at some of the other ones here. We got Enceladus. This is a good one. This is an icy moon. And again, you can see that covered with ice. That's what you'd expect. You can have, as we move farther away from the sun, things tend to be made of less rock and more ice, because you can have ice permanent once you get outside the orbit of Mars, for example. One of the interesting things about Enceladus is it has active geysers on its surface that actually spit out water vapor into space. And that's an indication that it can't be anywhere near billions of years old, or it would have run out of heat. It has to have a heat source to be able to do that. And there's no known mechanism that could keep that going for anywhere near billions of years. And so Enceladus is a very young moon, and that should be very clear. I want to go back to Saturn here for a second to point out something that I meant to mention earlier. But God was very kind to tilt this planet, contrary to what you'd expect in the secular model. In the secular model, really the planets, you'd expect them to all be upright, because they all formed from that same cloud. They all ought to be spinning in the same direction with the same rotation axis. But God tilted it by quite a bit so we could see the rings. Now, if he didn't do that, you really would not know that the rings are there, because they're very thin. They're millions of miles across, or not millions, but they're very long, but they're only maybe a mile or two thick. And so you would not see them. Now here, of course, you can see the shadow of the rings because we're still tilted relative to the sun. But if Saturn were not tilted at all, you wouldn't see even the shadow of the rings. They would just be gone. And that does happen every 15 years because Saturn, as it orbits the sun, in perspective from Earth, it goes edge on. And there's a period of a few weeks where Saturn is ringless. And it's interesting to see that. And then you can spot the moons because then the moons are all lined up. Okay, let's go to the next moon out here. Tethys is the next one out. Well, the next one that I selected. So there's Tethys, pretty ordinary. That's kind of what you'd expect a moon to look like, not too different from ours. Then we've got Rhea. Again, these are ones that you can see. Most of these you can see in a small telescope, a backyard telescope, if you know right where to look. And since these moons orbit in the plane of the rings, you'd have difficulty seeing the rings of Saturn if you lived on one of these little moons. Now, the moon that really has everyone's attention is Titan. And for a while, this was thought to be the largest moon in the solar system. It's not. It's the second largest. Ganymede wins out. So here's Titan, and nothing looks like Titan. It is an orange moon. Very strange. And that's because it has a very thick atmosphere, which is also unusual for a moon. Titan's the only known moon that has a thick atmosphere made of hydrocarbons. So of course, gasoline is a hydrocarbon, so that kind of stuff is what the atmosphere is made of. So gasoline would be very cheap on Titan. But oxygen would be expensive, so count your blessings. Once you remove the atmosphere, you can see the surface of Titan, which we've mapped using radar, again using spacecraft that have flown past it. And you notice sometimes you'll have an area that's very low resolution. That's because the spacecraft was far away when it measured that side. And then as it gets closer, it gets the higher resolution stuff there. So if you see that, that's why that's happening. So you can see why they thought Titan might be bigger than Ganymede at one point, because that atmosphere kind of puffs it out a little bit. It's like a cat when it gets upset, it kind of gets a little bigger. But it's actually, the actual surface of the moon is smaller than Ganymede. So there's Titan. Really interesting and strange moon. Nothing like it. Nothing like it. Another moon I want to point out that I think is really interesting is it's called Iapetus. And so we're going to go there next. But the thing that's interesting about Iapetus is astronomers could see it when it was on the right side of Saturn. That would be your right side. But they could not see it when it was on the left side of Saturn. It seemed to disappear every time. When it's on the right side, you can see it. When it's on the left side, you can't. What's going on? And of course, when telescopes got bigger, eventually they could see it on both sides. But it's a lot brighter when it's on the right side. So what's happening there? Well, most moons are like our moon. They're tidally locked. They keep their same face pointed toward the planet. And there was an astronomer who realized that's probably true of Iapetus. It probably keeps its same face pointed towards Saturn, which means when it's on one side of Saturn, you're seeing one side of Iapetus. When it's on the other side of Saturn, you're seeing the other side, right? What if one side's light and one side's dark? That would explain it, wouldn't it? Well, we've now sent spacecraft there, so we can determine if this is the case. So here's Iapetus, and lo and behold, it's white on one side and very dark on the other. Isn't that interesting? Got a light side and a dark side, like the Force or an Oreo cookie. White as snow on that side, amazing. And then we think there's particulate matter that's impacting this side and kind of covering it up like soot. It's got a chain of mountains, too, that are right along, just exactly along the equator, which is very interesting. And I don't think there's a good secular explanation for that either. It's almost like God just took it and went poof, and just kind of pushed it a little bit, and the equator popped out. Because it's exactly what it looks like. I thought it was an imaging artifact for years, but it's not. It's real. Well, let's see. Where else should we go on Saturn? I'll show you a couple other moons that I think are really interesting. Let's go back to the current time and go to... we're going to go to Epimetheus. Okay, this is a little bit of a tangent, but it's just too fascinating not to tell you about it. It's just cool. So here we have Epimetheus. And you can see it orbits pretty close to Saturn, remarkably close. And you can see its orbit there in red. Now, the orbit that's just inside it is the orbit of another moon, Janus. So Janus and Epimetheus, their orbits are very similar. But Epimetheus orbits just a little bit further out, which means it orbits a little bit slower, right? Because the closer a moon is, the faster it orbits. You saw that. So that means at some point, Janus, since it's orbiting faster than Epimetheus, Janus will have to pass Epimetheus. And you're thinking, that looks awfully close, right? And maybe you're hoping, well, maybe Janus is small enough that it can just skim by there. But in fact, Janus is larger than Epimetheus by quite a bit. Let's go to Janus here. Quite a bit larger. So much so that it actually covers both orbits. Now you can see Janus is on the inside track there. Its center goes through the inside track, so it's going to orbit a little faster than Epimetheus. And so they ought to collide. And if you do the math, even if you started them out with Janus just a little bit ahead of Epimetheus, it would take 4 years for it to eventually come around and collide. 4 years is the difference in their orbital paths. That's how long it takes for one moon to catch up with the other. So how are they still there? And this was a perplexing puzzle when it was first considered. What's the solution? Well, let me show you. Let me show you what happens. It's absolutely remarkable. So again, you got Epimetheus on the outside track, right? So it's moving a little slower. You got Janus on the inside track, so it's moving a little bit quicker. And so if I speed up time, you can see the moon's orbiting here. You can see, okay, so there's Janus, and there's Epimetheus, right? And their orbital speed is almost the same, because they're almost on the same orbit. And moons inside that orbit quicker, moons outside that orbit slower. We get that. Now what I can do is I can rotate with Janus and Epimetheus so that they look like they're stationary. Okay, let me show you how that, does that kind of make sense there? So they look frozen, right? And the moons that are inside them orbit faster. And the moons that are outside seem to be going backwards because they're orbiting slower, because we're rotating with Janus and Epimetheus. And they look pretty close to stationary, right? Because we know their orbital speed is very similar, but we do know that Janus is just a little bit faster. And so eventually it's going to catch up with Epimetheus. And Epimetheus is just a little bit slower, so eventually it's going to fall back, and you'd think they would collide. So let's watch what happens when we speed up time here. They're getting closer. Closer still, about to collide. Here we go. Well, now, wait a minute here. Well, no, wait a minute. Epimetheus, right? Epimetheus was on the outside track, so it should be orbiting slower, but now it's orbiting faster. What's going on here? Well, let's go back to Epimetheus. Is it still on the outside track? Let's have a look. It's now on the inside track. Now, how did that happen? Well, when these two moons get close, when Janus gets close to Epimetheus, and it's about, I guess from your perspective, it'd be like this. When it gets close to Epimetheus and it's about to collide, you would think, these moons have gravity. And the gravity from Epimetheus pulls forward on Janus, which moves it up. And the gravity from Janus pulls back on Epimetheus, which drops it down. And the two moons swap orbits. Every 4 years, they avoid collision by swapping orbits. Isn't that remarkable? It's the only place we know of that does that in the solar system. So really just fun to see, actually. At least I think it is. Isn't that ingenious? Now, admit it, you never would have thought of that. I certainly would have. I certainly wouldn't have. That's something that just reveals the creative diversity of the Lord. So let me do that again just so you can see it. And we'll let it go this time. You can see every 4 years, they just avoid collision like that. Every 4 years. Remarkable. That's so bizarre. I didn't even believe it until I actually wrote a computer simulation that simulates their gravity, and that's exactly what they do. It's phenomenal. Anyway. Oh, the Lord is awesome. The Lord is awesome. Okay, next out we have the planet Uranus. And this one defies all of the secular expectations too. One of the things we're going to see about Uranus, this we visited with spacecraft in 1986. Voyager 2 is the only spacecraft to have visited Uranus. It flew past it in 1986, and we got these wonderful images of a very blue sphere, very featureless. Now, sometimes clouds will form on its surface, but the wonderful images we got when Voyager 2 flew past it was a cloudless day on Uranus, and so the really good images you see, they don't show that so much. Now, the thing that's interesting about Uranus is it's tilted on its side. So you're looking at the North Pole of Uranus, and it's pointed right at the sun, as it was in 1986. Okay, so it's tilted on its side, which again is just totally contrary to what you'd expect in the secular explanation, where all the planets really ought to be upright and spinning the same way. At least they ought to have formed that way. And you can't imagine how Uranus could have suddenly, been tilted like that. It just defies secular logic. It has a magnetic field that's quite strong. In fact, my friend Russ Humphreys actually predicted the magnetic field of Uranus before it was measured by the Voyager spacecraft based on its biblical age of 6,000 years. He said based on 6,000 years, it should have decayed to this amount, and they flew past and it measured this amount. He was right on. The secularists were way off because they were assuming it's billions of years old. And so the magnetic field will be gone by now. Not only is it tilted on its side, but the moons are nice enough to orbit on their sides too. So they follow suit and orbit right around the equator of Uranus. At least the inner ones do that. But there's always, it's just interesting to see that too. And you can see at least there's 5 big moons that can be seen with a telescope from Earth. I've seen 3 of them with a modest-sized backyard telescope. They're very, very faint, but they're there. And I'm not going to spend a lot of time on this one, but I do want to show you at least one. I want to show you Miranda. Miranda, Ariel, Umbriel, Titania, and Oberon are the big 5. You may have noticed they're named after, a lot of them are named after Shakespearean characters, which is unique. The planet Uranus was discovered by William Herschel, an Englishman, and in honor of that, they named the moons after Shakespearean characters, or Alexander Pope's The Rape of the Lock. There's Miranda, very strange. It's got this weird reverse check mark on it. It looks like it's been bashed and reassembled. I mean, it's just a strange little moon, and it's fun to watch these things. And I point out, too, that for this system, we only know what the northern hemispheres of these moons look like, right? Because they're all orbiting with their north pole pointed toward the sun. So the south pole is in darkness. You can't see it. And we'll probably never know what the other side looks like unless we send another mission back to back to that planet. Uranus is about 4 times the size of Earth in diameter, and it's sort of a gas giant with some ices as well. Very kind of similar to Jupiter and Saturn, really, in many respects. So that's Uranus. It does have a ring system. All the big planets, Jupiter, Saturn, Uranus, Neptune, they all have rings, but only Saturn's are thick enough to be easily seen from Earth. Next up, we have Neptune. Now, Voyager 2 flew past Neptune in 1989. I remember that happening. I was pretty young, but I remember it, and it was very exciting for me because we were, seeing another planet for the first time. You just can't get good images of Neptune from Earth. At least you couldn't back in the 1980s. And so this was the first time that we knew up close what this planet looked like. And we were delighted to see that it has a great dark spot, much like Jupiter's red spot, an enormous hurricane or cyclone that's rotating around there. Unlike Jupiter's red spot, that one is not permanent. It comes and goes. And we know that because Hubble has the ability to do almost as good as Voyager, not quite. But Hubble has shown that spot goes away from time to time. Sometimes another one forms in the northern hemisphere, and then it goes away. And so it's not quite as stable as the Jupiter system. And you don't see much in the way of belts and zones. They're there, but they're very faint. They're more sublime than Jupiter's. So that's Neptune. Neptune, again, has a strong magnetic field, which is an indication that it can't be anywhere near billions of years old, or that magnetic field would have decayed a long time ago. And it also has internal heat, like Jupiter. It gives off actually proportionally more than Jupiter does. It gives off 2.6, 2.7 times as much energy as it receives from the sun. And that can't happen over billions of years, or they would have lost all that energy long ago. So you see how all these worlds indicate that they're nowhere near billions of years old. The evidence is there that they line up with the biblical time scale. Let's take a look at some of the moons here. You can see the inner moons, they kind of obey that rule, right? But there's always one oddball, right? And in this case, it's Triton. Triton just breaks all the rules because it's a big moon, and big moons always orbit in the equator of their planet, except for ours. Ours is an exception, and Triton's the other one. And big moons always orbit in the same direction their planet rotates, except for Triton. It's exactly backwards. And in fact, if I speed up time, you can see that. All these moons are nice and neat and obeying the rules, and then Triton is just going exactly the opposite, just to be different. Let me look at it from overhead here so you can see it. That's a little bit too much. Let's zoom in some. See? Just backwards. Fortunately, it's one of the moons that Voyager 2 flew past, and it got one side in low resolution when it was still far away, but it got the other side in incredibly high resolution. And boy, were the secularists surprised to see some of the features on Triton. Triton has a very thin atmosphere, and it has geysers, nitrogen geysers, and they carry soot with them. And you see these little black streaks on there. There are these little black smokers all across the surface of Triton. If I zoom in on those, you can see them a little better. What happens is the geysers shoot up this material, and then the wind carries it and it deposits it, and it forms streaks, these horizontal streaks, as the wind carrying that soot there. Isn't that fascinating? And see, to have something like that, it means you have to have internal heat. And you can't have internal heat over billions of years because there's nothing to generate it out of that distance. It's far away from the sun. It's 30 times farther away from the sun than Earth is. And so you just don't have a source of energy to do that. Isn't that a wonderful little moon? Just breaks all the rules. Little rebel. And then, like all the other systems that we've found, the inner moons, except for Triton, obey the rules. The outer moons kind of do what they want. They can orbit in different paths, you see there. Nereid was one of the first that was discovered that has a very elliptical orbit around its planet. You can see that there. But they've found some other ones now that do that as well. So that's the Neptune system. Isn't it neat that we've visited these worlds? Just incredible. Well, it was really exciting last year, 2015, in July, because we saw Pluto for the first time up close. Now, Pluto is quite different from the planets. In fact, it's been demoted from planethood. You might have known that. It used to be considered the ninth planet. You can see it's different, though. Its orbit's not in the same plane as the planets. It's not terribly far off, but it is off. Its orbit is a lot more elliptical than the planets. In fact, Pluto's orbit occasionally crosses that of Neptune. Now, they could never collide for two reasons. First of all, they're in different planes, okay, and so the paths never actually intersect. And the other reason is that Pluto orbits in resonance with Neptune. So when Neptune orbits 3 times, Pluto orbits twice, which means they're never close to each other. That seems to be a design feature as well, interestingly. But yeah, from I think it was 1977 to 1999, Pluto was actually closer to the sun than Neptune by a little bit. And that won't happen again in your lifetime. No matter how many vitamins you take. That's not gonna. Well, let's go visit Pluto. New Horizons spacecraft launched in 2006, about the size of grand piano, and it flew past Pluto and got, of course, one side, when it's still far away, it's getting images of that side. You can see it's got some craters on it, kind of interesting. But, of course, that's much better than Hubble can do because Pluto is tremendously far away, and Pluto is smaller than the moon. This is not a big world. And it's one of the reasons why it was demoted from planet status. And by divine providence, as New Horizons got closer and closer to Pluto, it got the really interesting side with all kinds of wonderful features on it, including this huge heart-shaped structure, Tombaugh Regio, they've named that. So isn't that wonderful? And absolutely contrary to secular expectations, because the secularists were expecting that Pluto, being a cold, dead world, 4.5 billion years old, ought to be just totally saturated with craters at that point. There can't be any heat source at that distance. It's much, it's 30 times farther away from the sun than Earth is, even at its closest points, 29, something like that. And there's no radioactive elements at that distance that would provide a power source, at least not very many, because Pluto's made of the light stuff, ices. And so they were not expecting any geology. They were just expecting a world saturated with craters. And there are a few craters on Pluto. We'd expect that because there's lots of stuff orbiting out there. And Pluto has only a thin atmosphere, so most stuff that comes near it would impact. But you can see in this region right here, there's not a single crater. This is Sputnik Planum. There's not one crater in there. Isn't that interesting? Now, that just wouldn't be if that surface were billions of years old, which means the surface is recent. And even the secularists have conceded, yeah, you got to have a recent surface. But how do you make one if the moon is frozen and has been for 4.5 billion years? You have to have some kind of geology to produce whatever that is. And we've never seen terrain like that before. It's another little Easter egg that the Lord put out there for our enjoyment. No one has seen that. You see those like little polygons that are connected like that, like a little jigsaw puzzle that's been put together? It's fascinating. Nobody had ever seen that before on any of the worlds, any of the other worlds of the solar system. It has mountains, which was not expected. Mountains made of ice. At that distance, ice is very cold and as hard as rock. And so you can make big mountains out of them. They're big as the Rocky Mountains, but they're made of ice. You can see some of them there. It has its own unique beauty to it, really. And Pluto is orbited by a moon half its size called Charon. And of course, we got good images of Charon as well. New Horizons went past that, at least one side of Charon. And there's the cool side right there. And again, you see some craters, but you see a lot of evidence of geologic activity, mountains and canyons, and totally unexpected from the secular viewpoint. And a dark North Pole, which we've never seen before either. We still don't know exactly what's going on there. But isn't that fascinating? Just these little gems that the Lord's put out there that remind us that He's creative, He's diverse, and He is not under any obligation to make things according to the way secularists would expect. He does things very differently sometimes. Let's zoom out a little bit here. Charon is actually so large compared to Pluto that both objects orbit around their common center of mass. You see that? So it's kind of like the teeter-totter. You know, the big kid has to sit a little closer to the center, you know, to get it to work right. And so Pluto gets moved just a little bit, and Charon gets zipped around. But Pluto, their center of mass is actually outside of Pluto, and that's not true for any planet. So that's another reason to think that this is a different kind of object. He's got some other moons out there too, 5 in total, but the other ones are tiny. They're just large boulders in space, basically. Charon's the only one of any significance. So isn't that stunning? And again, what a privilege. Just a few years ago, I couldn't have shown you those images. The best images we had of Pluto looked like that a few years ago. That was it. Hubble can't do much better than that. So that's the Pluto system. Now, there are lots of other objects in our solar system besides planets. We had dwarf planets. Pluto's a dwarf planet now. We got asteroids. Let's see if I can turn on the asteroids here. That's not what I wanted. Oh, I crashed it. There we go. There's the asteroids. Most of them orbit in between Mars and Jupiter, and they have different kinds of orbits. They're not as constrained to the plane of the solar system as the planets are. We visited a few of the asteroids. We visited Ceres, for example, which is the largest. That's not what I wanted. Why is it doing that? Come on. Sorry. Thought I had all the bugs worked out. Nope. Guess we're not going to Ceres. Let's do it this way. Let's see. Ceres is the largest asteroid, the first discovered. It was discovered in 1801. It was classified as a planet when it was discovered. And this is one of the ones we visited with spacecraft, and so we know what the surface looks like. And pretty unremarkable. It looks kind of like a moon, really. There's one feature on it that's kind of interesting, where it's incredibly white, and we don't quite know what that is. But isn't that interesting? Very, very bright. Ice, maybe. In any case. So asteroids are pretty unremarkable. They're star-like in the sense that when you look at them through a telescope, they just look like points. You can't see any size to them. That's where they get their name. Asteroid means star-like, basically. So we have comets, too. I do want to show you comets briefly. Comets are like cats. They have tails and they do what they want. They tend to have very elliptical orbits. They go very far away from the sun, and then they whiplash back in. You can really see Kepler's second law in action when we speed up time here. Let's speed up time, and you can watch Comet Borrelli there. When it gets close to the sun, you see how it goes much, much faster? Halley's Comet, which last visited us in 1986. You can see it orbits backwards. Again, comets do that sometimes. And it's going to come in and just watch how it whiplashes back out. Zip. Really quick. So it doesn't spend much time in the inner solar system. And if it did, it would be gone, right? Because ice can't remain close to the sun very long. Every time you see a comet, you know that the solar system is not billions of years old, because comets cannot last billions of years. That icy material is disintegrated as they get close to the sun. And so comets like that are an indication of a young solar system. You can see some of them go really far out of the solar system. Hale-Bopp, for example. Hale-Bopp's orbit is about 4,000 years long, something like that. And I forget the exact number, but I did the math at one point. How many of you saw Hale-Bopp back in 1997? Okay, yeah, a few of you. I saw it too. It was a wonderful comet. The last time that visited the inner solar system, it was probably seen by Noah. Isn't that interesting? A very young Noah. Well, anyway, we live in an amazing solar system. God wasn't obliged to make it interesting. All he had to do was make the earth, right? And maybe the sun and the moon for tides. But he made all these wonderful objects for us to enjoy and appreciate. And when we come back to our own world, we see the special beauty of Earth. Earth is really just stunningly beautiful. And it's designed for life, and God formed it to be inhabited, the Bible tells us. And of all these planets that we've studied, this is the one that Jesus Christ came to and became human being to take our place on the cross. Very special and humbling to think of that, you know. In a size perspective, we're just nothing. We're nothing. And yet God cares about us. This is the one that he came to. Isn't that fascinating? And just, it really gives you a sense of kind of humble boldness, you know. Humble because we're nothing, and yet God cares about us. That's awesome. That's really awesome. Well, there are a number of resources I encourage you to get. Let me exit out of here. And the book that most covers what I've talked about today, Taking Back Astronomy, and it's going to show you apologetically how all these things work. That's a great resource. Stargazer's Guide to the Night Sky, if you'd like to know how to find these planets, well, that's going to show you how to do it. It's got beautiful full-color star charts showing you how to find these things. And you say, I don't have a telescope. It doesn't matter. There's a lot of stuff you can see naked eye. A lot of stuff you can see with binoculars. You know, even Saturn's rings, you can see barely. You can see them with binoculars. You just got to know which one's Saturn. And that's where the book will help you out, because it's going to help you distinguish that. So that's a great resource I'd encourage you to get. And we have that out at the tables there. You want the best of everything, Creation Basics and Beyond, written by all of our staff scientists at ICR. And we have a student version as well that you're welcome to get, the Guide to Creation Basics. Ultimate Proof of Creation, if you want a bulletproof argument for biblical creation, this is it. This is the one I'd encourage students to get before they go off to college. It really will help you to think clearly, biblically, about the issues and give an ultimate proof, an irrefutable proof of creation. Understanding Genesis. Do we know that the days of creation really are ordinary days? Is it really true? Does the Bible really have to mean 6,000 years or something like that? Well, that book will show you that, yeah, the Bible really does mean what it says, and it'll show you that you can demonstrate logically that Genesis really does mean what it says. Discerning Truth, How to Spot Logical Fallacies and Arguments That Evolutionists Make. That's a great resource that I'd encourage you to get as well. We have a number of videos. We have one on where I'm talking about astronomy. I'm not sure if we have this one tonight. We might have it. Created Cosmos, where it takes you on a tour of the solar system. We've got The Secret Code of Creation. Remember that little thing you saw when you first came in on the fractals and the Mandelbrot set? There's a whole DVD on that topic out there. It's called The Secret Code of Creation. That's a lot of fun. And you can see these shapes that God has built into numbers. And they're beautiful, stunningly beautiful, and there's no secular explanation for them. None whatsoever. One of my favorite books that we have at ICR is Dinosaurs, Marvels of God's Design. And of course, if you came last week and learned about dinosaurs, you'll want to follow up with this textbook. It really is a wonderful resource, an easy read, but it's very enjoyable and gives you the details as well. So don't forget to sign up for Acts and Facts if you haven't already. We have the sign-up sheet out front. And again, check us out at icr.org. And I really encourage you to check out that website. It's a great resource. Now we're going to take a 15-minute, some people call them a bathroom break. I call it a book buying break, okay? I want you to go out and get the resources. It's really important that you get this information, and I'd encourage you to check that out. And that's only going to be available during the break. Then we're going to do a Q&A. After the Q&A, the books aren't going to be available anymore. So get them now. Get them while they're hot, okay? We'll see you back in 15 minutes. Does that sound good? Okay, thank you very much. Really appreciate it.
I believe in the sun.
said. Another day I replay. One too many doubts inside my head. Am I strong, beautiful? Am I good enough? Do I belong after all that I've said and done? Is it real when I feel I don't measure up? Am I loved? I'm running to the one who knows me, who made every part of me in his hands. I'm holding to the one who holds me, 'cause I know whose I am, I know who I am. I am sure I am yours. Turning down, tuning out every single word that caused me pain. Unashamed and unafraid, 'cause I believe you mean it when you say I am strong, beautiful, I am good enough. I belong after all 'cause of what you've done. This is real, what I feel, no one made it up. I am loved. I'm running to the one who knows me, who made every part of me in his hands. I'm holding to the one who holds me, 'cause I know whose I am, I know who I am.
All right, we're going to start in about 2 minutes, so if you will find your seat, we've got a lot of wonderful questions, and we've got an expert here to ask them to. So in about 2 minutes.
Fearfully, wonderfully, perfectly, you have made me. I'm running to the one who knows me. Yeah, I'm holding to the one who holds me, holds me, holds me.
All right. We're going to go ahead and start with our questions and answers here. We've got an expert witness here, and we'll try to stump the expert. How about it? All right. How about this? Let's start off with the Big Bang Theory. I hear a lot about the Big Bang Theory, and even some Christians say that the Big Bang is a good apologetic for creation, a moment of creation, in that it points to a beginning. What do you have to say about that?
I think we need to be honest in the way that we approach apologetics. And the Big Bang is not true. It just isn't true. It's contrary to what the Bible teaches, first of all. It's not good science. It's not well backed by science. I do other talks where I point out problems with the Big Bang and how it doesn't match up to good scientific thinking. And so to use something that's false to try and push people to something that's true, I don't think that's a good approach. We need to be faithful to the faith that we're trying to lead people to. What you lead people by is what you lead people to, really. And so we want to make sure that we're truthful and consistent with the scriptures and everything that we teach. It is true that the Big Bang claims that there's a beginning, but there are lots of other creation myths that are contrary to scripture that indicate there's a beginning. I mean, fictional stories, The Lord of the Rings has a beginning, but that doesn't mean that I should use that and teach that as if that were true in order to try to convince people that the Bible's true.
So really, you're just simply saying that the evidence does not support it.
The evidence doesn't support the Big Bang, of course, and more importantly, it's contrary to Scripture. And
there's a question of whether or not it has any creative ability anyway, whether or not there's evidence of an expanding universe that goes back to the beginning. What is the mechanism for ordering all this together blindly through the forces of nature?
Yeah, well, the one thing the Big Bang doesn't explain is the origin of the universe, ironically. Okay. It's a story about what allegedly happened afterwards, but in terms of how the singularity allegedly got there and how it suddenly began to expand, there's no explanation for that. There's no reasoning behind that, really. The Big Bang is designed, you need to understand, the Big Bang is designed to explain how the universe could come about naturally. Okay, now that's not to say everyone who believes in the Big Bang is an atheist, but virtually all atheists have to believe in the Big Bang or something like that because they don't want to believe in God. Once you allow God to do what he says he's going to do, or once you allow him to exist as if he needed our allowance to do that, then there's no reason to think that the universe was created in a naturalistic fashion. God upholds the universe today in a way that's so consistent we can write down equations, and we call that natural law. That's the normal way God upholds the universe. But he's under no obligation to create the universe in that way. And we know from Scripture he didn't. He spoke things into existence. That's something he's not doing now. You need to understand the Big Bang is contrary to the Scriptures. Not only the time scale is way off. The Big Bang is billions of years. Scripture's 6 days. The order of events is different. The Big Bang has the stars evolving long before the Earth. The Bible has the Earth being created before the stars. So the order is different. It's contrary to the Bible. And that alone is reason to reject it. The Bible's demonstrated itself to be true. And we haven't learned the lesson of history if we're going to say, yes, but the Bible's wrong about this. We finally figured out, more than God does. But scientifically it has its problems as well. And I've written on that topic.
Good. Is there any evidence from reliable astronomers of objects in the universe being older than the universe?
Oh, of course you can't...
First of all, explain the tension there, that the scientists are alleging that the universe is certain, it's 13.8 billion years old. Then all of a sudden they analyze certain objects, and it looks like maybe, in fact, they're older than 13.8 billion years. How can that possibly be?
Right. First of all, you can't determine the age of something scientifically, right? Age is a question of history, and science is about how the universe operates today. Now, that's not to say you can't use scientific techniques to make a guess about the age of something. Certainly we can do that. But that always involves assumptions, And so what happens is secularists, in some cases, they'll do a particular age calculation, age estimation on something, say the universe, assuming the Big Bang, assuming they'll get 13.8 billion years. And then they'll do an age calculation making their same assumptions on something else, and they'll find that it's a bit older than the universe, which is a problem in their view. And what that tells you is that their assumptions are wrong. That's the bottom line. You can't have a universe containing things that are older than the universe. It doesn't make any sense. And there are situations where that's happened. There are certain Stars or star clusters where they've estimated the age to be older than 13.8 billion years. There's been one recently. I forget the details of it, so I'll mess it up if I try to remember the details. But in any case, there are a lot of examples of that where they'll find something that, by this calculation, it's contrary to this calculation, and that just tells you their assumptions are wrong.
If you could land on Jupiter or another gas planet, suppose you're a superhuman and you could do so, would you fall through it?
Yeah, Jupiter is, it's a ball of gas. It probably goes liquid at some point because the pressure increases. Theoretically, you could go through Jupiter in principle, because it's, now it gets thicker and thicker as you go in, and so it might be like molasses at some point, but there's no solid surface to land on. So yeah, you couldn't land a rocket ship on Jupiter really, but you could, theoretically, you could go all the way through it in principle.
Okay. What keeps Earth's atmosphere from flying off? Or does it lose some of its mass at times?
Yeah, the Earth's atmosphere is held by gravity, so the atmosphere, you've got these atoms, they want to fall toward Earth's surface. The lighter the atoms are, the less the force of gravity on that atom, and some of the atoms can get kicked up pretty high in the atmosphere. The main elements that are necessary for life, they're pretty permanent. We're not really bleeding off anything like oxygen or nitrogen. Light stuff like helium can escape into space. It can, especially when there's a solar flare or something like that, where the sun kicks up, or coronal mass ejection, and that can carry off little bits of helium. And so we might lose helium eventually, but the important stuff that you need to live, it's permanent. It's permanently bound by gravity.
Okay. How do we measure the speed of light and distance, all these estimates of distance of how far that quasar or that galaxy or that cluster are? How do you do that?
Yeah, okay, two different issues. The speed of light, we can do that in a laboratory. In fact, one of the projects I did as an undergraduate is I measured the speed of light in a way that's a little bit unconventional. But there's different ways you can do it. But effectively, you send a light pulse out, bounce it off a mirror or something, bring it back. You measure the time difference between emission and reception. You measure the distance. You divide distance by time. There's your speed of light. So that one's easy. How do we get the distance to things in space? That's a little bit tricky because there are several different methods that you use. Space is so enormous that you can't use any one method over the entire range of distances in space. Most distance calculations work over a limited range, okay? And then you have to, you bootstrap them. You have to use one to get to the next and so on. And they overlap, so you can calibrate one to the other. Things that are very nearby, we can bounce light or radar off of them. And so we know the distance to the moon within a fraction of an inch because we can bounce a laser off it. We know it very precisely. We've measured the distance to Venus using radar. You can bounce radar off of Venus. And based on the time delay, you can get the distance to that. For nearby stars, you use parallax. When the Earth's on one side of the sun and it looks at a nearby star, it looks like it's over there. When the Earth's on the other side of the sun and it looks at the same star, it looks like it's over there. The star seems to shift a little bit depending on which side of the sun the Earth is on. It's a small amount because stars are very distant. But for the nearest stars that are less than 2,000 light years away, you can measure that shift, at least with the spacecraft. You can measure that very slight shift that occurs. That's parallax when the Earth is on one side of the sun versus the other. It works out to about 2,000 light years. Beyond that, you have to use other methods. Some are easy to understand, others are a little more complicated. There's the moving cluster method, where you look at the angular velocities of stars in a cluster and you compare that to their Doppler velocity, which is forward, and that allows you to calculate the distance. That's getting a little bit complicated. One of the ones that I think is easier to understand is called a standard candle method, and that's where you find an object that has a known brightness, such as an RR Lyrae star or a Cepheid variable star. RR Lyrae stars, we can recognize them because they pulsate, and they have this very particular kind of pulsation, and we've learned to recognize that. And when you find an RR Lyrae star, it turns out they're all the same brightness, and we know that because there are some within that 2,000 light year radius, and so we know the distance, and we know how bright they look. We can calculate how bright they really are. So if you find an RR Lyrae star, you know it has this certain brightness. Then what you do is you say, but how bright does it look? Because our earlier stars that are closer will look brighter, those that are farther will look fainter. And you can use the inverse square law, the fact that light falls off as 1 over distance squared, to calculate the distance to that particular object. That's called a standard candle method. So you have an object that has a known brightness, and you look at how bright it looks, and that tells you something about the distance. And that'll get you very far out. You can do that with, that'll get you out very far in the universe. And then with farthest stuff, you calibrate it with redshift. And some things we just don't know the distance very well. But those are some of the methods that you use. And if you wanted to learn more about that, you should look up the cosmic distance ladder. And that shows how those different methods overlap.
Okay. A couple of questions that build on your answer there. Do you believe that these objects that some scientists claim are 13.8 billion light years away in terms of distance, not age, but distance, do you believe that that's true, probably?
Yeah, I think the methods by which we establish the distances are really very good methods. They don't involve secular assumptions at all. They involve the assumption that God upholds the distant universe the same way he does here, and so we can use the same math here that we can use there. I think that's a very good, very reasonable presupposition.
Okay, so if that is the case, and light travels at 186,000 miles per second, which is, as I recall, what, how far is that? How far does light travel in 1 year?
It's about 6 trillion miles.
About 6 trillion miles. If that's the case, how are we able to see these objects if the Earth is only 6,000 years old? Did I understand? Did you guys understand the question?
Yeah.
If the objects are truly that far away and light travels at a finite speed, how in the world can we see these objects, since light wouldn't be able to get here if it only traveled 6,000 years? Or is there some alternative explanation?
Yeah, there's actually a few different ways that God could get the light here much more quickly. And there's some that I don't like, but let me just let's cut to the chase here. Light doesn't have to travel at the same speed in all directions. And it turns out that, for example, light could move as fast as infinity when it's moving toward you, provided the speed away is 1/2 c, where c is the round-trip average speed of light. Really, when you measure the speed of light, all the experiments that have been done to measure it, either directly or indirectly, are measuring a round-trip time-average speed. In other words, you send the light out to the mirror, and you bounce it back, and you find it takes, say, 2 seconds to make that trip, right? Now, most people would assume, well, it takes 1 second to go out and 1 second to come back, but you don't really know that. It might take all 2 seconds to go out, and no time at all does it back. And to make matters even more strange and counterintuitive, it turns out it's impossible to measure the one-way speed of light. This is called the conventionality thesis. It's something that's really pretty well established in physics. And the one-way speed of light is not something that is a property of nature. It's something we get to choose, which means we can choose the one-way speed of light to be different, whatever we want it to be, even infinite. And so it takes, if you make that assumption, if you make that choice, then it takes no time at all for light to get from those distant galaxies to Earth at all. It gets here instantly. We're actually seeing the universe in real time if you use that convention. And that's not to say that the other convention is wrong. They're just different. It's kind of like feet or meters. You can use either one to measure the length of a table, and you'll get a different number in terms of your answer. But the length of the table is what it is, okay? And it's like that with the one-way speed of light. You can choose it to be infinitely fast toward you, or you can choose it to be slower, whatever, within certain constraints, as long as you're consistent and all of physics will work. And this was demonstrated back in the 1970s. John Winnie showed that all of Einstein's relativity works without making assumptions about the one-way speed of light. It's really fascinating. And I think the Bible is using the convention that light, when it moves toward the observer, is instantaneous. And so using that convention, there's no distant starlight problem. God made the galaxies on day 4, and their light reached Earth immediately, and still is, using that convention. It's more complicated than that, but I don't want to, already your heads are ready to just sort of pop, and so I don't want to go into too much detail. But we do have that in my chapter in Creation Basics and Beyond. We have that a little better, a little slower explanation.
Great.
Yeah.
And there are other explanations trying to
Yeah.
sort through that.
There's several ways God could have done it. That's one way.
Okay, great. Creationists have an answer to that question.
Yes,
okay.
yeah.
Here's a really interesting one. Do you have a theory about the star that the wise men saw?
Yeah, I think it was a supernatural manifestation of God's power. There have been a lot of explanations for the Star of Bethlehem, and there's a popular video that goes around, and the guy's got good intentions, I'm sure, but I don't think he's right about it, where he claims that it was a conjunction of Jupiter and Venus, and that does happen occasionally. There was a conjunction is when the two objects come very close together in the sky, and there was a really good one on the year 2 BC. I think around June 17th is when it happened, where Venus and Jupiter came really close together. We know that because we can run computer simulations, and I've done that. And yeah, they really did. But does that fit the description in the text? And I don't believe that it does. First of all, we know that the wise men saw the star twice. Before meeting with Herod, because he asked them what time they saw the star, right, so he could assess the age of the child. And then after they met with Herod, it says they saw the star again and they rejoiced with exceedingly great joy. So they saw it on 2 occasions, but the conjunction of Venus and Jupiter happened only once. Sure. And so that it doesn't fit the description. Also, the text indicates that the star went ahead of them, indicating it moved. It went ahead of the wise men and stood over where the child was. And so no natural object will do that. So I think it was a supernatural and atmospheric manifestation of God's power, something relatively close to the ground, so that you could get an estimate of if you're really under it or not. And it just moved over and stood right where the child was, never to be repeated. Unique manifestation of God's power. God can do that kind of thing, and we shouldn't be bothered by that.
Scientists talk about objects called black holes. Do you believe in such objects, or if so, what are they?
Yeah, black hole, I do believe in them, and there's good reason to believe that black holes exist. They're predicted to exist theoretically on the basis of Einstein's physics, general relativity. Yeah, by the way, I have just almost finished writing a book on this topic, and it's going to be neat because I love black holes. Black holes are incredibly cool. They're not only a test of physics, but they show us something about the mind of God. They're mind-blowing. I mean, it's weird, but they're neat. They're basically regions of space where the gravity is so intense that light can't escape. And since nothing can go faster than light, it follows that nothing can escape a black hole. Once you're inside that, that's it, game over. And one way to make them is when a star collapses in on itself. We think there's good evidence that when very massive stars explode, now we know they do that, we see them explode from time to time, that the inner portions of it get compressed together, and once they get inside this point of no return, which is called the event horizon, once they get inside that, there's nothing that can stop them from compressing all the way down to a point. So all the mass in a black hole is in a little point in the middle, interestingly, of no size, because if it had any size, it would collapse in. But the region surrounding it, there's like a sphere that is there's nothing physical there, but you can imagine a sphere around it that is the point of no return. And once you're inside that, you can't escape. You're going to die once you get inside that. But there are none nearby Earth, and that's a good thing. So there's no problem for us.
Okay, I think many of us heard news reports about Planet X. Is there such a thing as Planet X?
Well, there could be planets that in our own solar system that we haven't discovered, but they would have to be either very small or very far out, very far away, because with modern technology, if they were bright and nearby, we would have found them by now. There have been a lot of systematic searches of the heavens, and we've discovered thousands of asteroids, and we've discovered these trans-Neptunian objects, which are a little smaller than Pluto, that are out at that distance, but they're not big enough to be classified as a planet. So if there was a planet out there, it would have to be really far away. And I don't believe there's any good evidence currently that there is one. Now, again, there could be, but you've heard these claims that, well, based on these certain calculations, that we think there's a planet out there. I don't think that that's well established. The calculations that they're doing assume millions of years, and so I don't have any reason to believe in their conclusion. Again, there could be one out there, but there's no reason at the present time to believe that there is one.
I guess this question's just asking you to speculate. Do you think that humans will ever colonize Mars or maybe even the moon?
I would really like to believe that, but I don't know. There's not a whole lot of good reason to go there. All the cool stuff's on Earth, right? In terms of the stuff that we need, all the stuff we need. The great restaurants are all on Earth. That's right. The best television shows are on Earth. What would you gain from going to the moon? Maybe you could mine it. I don't know. I think it would be neat. I'm all for human space exploration. It's very exciting. But there are a lot of challenges to overcome. You think, well, we went to the moon. Mars is the next step. Mars is a lot farther away than the moon, a lot farther. And the moon has the advantage that it is sometimes in Earth's magnetic field. And Earth's magnetic field surrounds us, but it gets pushed kind of by the sun, and it forms kind of almost like a comet tail, and the moon is sometimes in that. And it's good to be inside Earth's magnetic field because that protects you from cosmic rays. Cosmic rays are bad. Cosmic rays cause mutations and things like cancer and so on. In fact, the astronauts, they monitor them. They're only allowed to do so much spacewalks and things like that because there's a lifetime exposure limit where it would be dangerous to be exposed to radiation beyond that. Now, the astronauts in Earth orbit are mostly protected from a lot of that radiation. On the moon, not as much. But again, the astronauts on the moon were partly protected depending on where the moon was in its orbit. With Mars, you don't have that protection. The trip between Earth and Mars, you don't have that protection. There's no magnetic field there, and so you're exposed to cosmic radiation. That's going to be a problem. A trip to Mars could be as much as 2 years. Being weightless for 2 years, that can be a problem. Human beings were not designed for a weightless environment, and all sorts of nasty stuff starts happening to your body. Not only, your muscles atrophy at an alarming rate, your bones decalcify at a tremendous rate, at 10 times greater than the rate of someone who has osteoporosis. And so all these things can happen. And one of the main things they're doing at NASA, and in fact, I had a chance to talk with astronaut Jeff Williams just a few weeks ago on the space station. It was really neat. They hooked us up with NASA, and I got to see him float there and ask him a few questions. I asked him what experiments he was working on. He said one of the things that he finds interesting is how the human body responds to weightlessness. That's one of the main things they're studying on the International Space Station. And they've learned to compensate for some of these things. They've learned to compensate for loss of bone mass. There's certain medication they can take. They exercise 2 hours every day. They have to in order to just maintain muscle mass, not to get any new one. But there's still some other problems. For example, your eyes. Sometimes astronauts, their vision degrades when they're on the International Space Station. They think maybe because the pressure, normally your blood goes to your feet when you're in gravity, but in space it equalizes and that creates extra pressure on the optic nerve. All kinds of problems. We're not designed for outer space, we're designed for Earth. And I'm not saying it's impossible, but it's a lot more challenging than people think that it would be. And then when you get there, when you get to Mars, there's nothing there. You can't live off of Mars. You need to bring a good section of Earth with you to live there even for a period of time.
Wow. Is there proof for global warming?
Okay, there is good evidence that in the last couple centuries, the Earth's temperature has gone up by about 1 degree, something like that. It's not a huge amount. What really is questionable is what is the cause? And of course, the alarmists say, well, obviously, human beings have caused global warming. But I don't think there's any good evidence for that. We may have contributed slightly, but people say, well, we're putting out all this carbon dioxide. Well, carbon dioxide is a very minor greenhouse gas. And if you look historically at the times when human beings were putting out the most carbon dioxide, they do not correlate with Earth's temperatures. If you think of carbon dioxide was the cause, the Earth temperature would go up, right? And you don't find that. You just don't find that at all. Now, there is a correlation between carbon dioxide in the atmosphere and Earth's temperatures, but it's the reverse of what you'd think. You see, what happens is ocean water contains carbon dioxide in it. And when you heat up the ocean, it releases that carbon dioxide. So what happens is first, Earth's temperature goes up a little bit, and that releases carbon dioxide into the atmosphere, and the carbon dioxide goes up. And so the people say, see, there's a correlation between the two. And then the temperature goes down, and the carbon dioxide redissolves in the ocean. So there is a correlation, but it's the cause and effect is reversed. It's the Earth's temperature that's causing the CO2 to go up or down, and not the reverse. So I don't think there's a lot of good evidence that human beings are responsible for global warming. And we need to remember something too. The Bible promises us in Genesis 8:22, God promises that the basic cycles of nature will be in the future as they have been in the past, as long as the Earth remains. And so that indicates that there cannot be any kind of catastrophic global warming. We have a promise from God that can't happen.
Interesting. Is there reason to think that God created other people on other planets? If so, do they sin? And if they sin, does he provide salvation?
Yeah, those are great questions. And I don't think that he did create people on other planets. Now, I'm a sci-fi buff. I love stuff like Star Trek and things like that. But I don't think the real universe is that way. For one thing, the problems there that are raised, if you think about, well, what happens if the Klingons sin? Well, the problem is they can't be saved because, you see, it's because we're related to Jesus Christ. It's because he became a man that he can substitute for us on the cross. It's because we're related to him. In fact, it's a biblical law that only a kinsman can redeem you. Only a relative can redeem you. And so that's why Jesus can atone for our sins on the cross. But Lieutenant Commander Worf is out of luck because he's a Klingon. He's not related to Jesus. And so he can't be saved. That's a problem. You say, well, what if the Klingons never sinned? Well, then it's a problem because they're still suffering the effects of the curse. All creation groans under that bondage of corruption. And some people say, well, maybe Jesus went to the Klingon homeworld, became a Klingon to die for them. But no, the Bible says he died once for all. He was raised incorruptible, which means he's never going to die again. So as much as I like sci-fi, Earth is very special. It really is.
Okay. What do you think is the biggest scientific stumbling block for secular scientists?
Oh, in coming to the Christian faith?
Yeah, with respect to the creation account, with
Okay.
respect to Jesus, the Bible, or what do you think is the biggest stumbling block?
Well, it's interesting. The biggest stumbling block isn't an intellectual one at all. It's a heart problem. And I'm not referring to the physical heart, but the core of your being, your spirit. The Bible tells us that unless the Holy Spirit opens your eyes, you can't say that Jesus is Lord. No man can say that Jesus is Lord except by the Holy Ghost, the Bible says. And we have this sin nature. We're descended from Adam. We're born with a tendency to want to rebel against God. We're rebels against him. We commit high treason against him. We hate him. We spit at him. We don't want to live by his law. And so when people see evidence for God, they are highly motivated to not believe it. And you need to recognize that. That is a very real phenomenon. A lot of times atheists will like to say, well, I'm very neutral. If only there were enough evidence. I would love to believe in God if only there were enough evidence. The Bible says they're lying. The Bible says in Romans 1, verses 18 through 20, everyone is aware of God. Everyone knows that in their heart of hearts. And people work very, very hard to suppress that truth and unrighteousness. Very hard. And so they come up with all kinds of rescuing devices. The biggest stumbling block is they don't want to believe. That is the biggest stumbling block. Now, I think there are intellectual ones that are prominent that they use to try and suppress that knowledge of God. Distant starlight would be one. They'd say, how can the universe really be, thousands of years old when you got these galaxies so far away? But I point out, actually, if you understand the physics of Einstein, that is not a problem. That is not a problem. Or, we know radioactive elements decay in the Earth's billions of years. Billions of years is one of the big ones. And then evolution is the other one that they try to use. Those are the main, in terms of the intellectual arguments that they try to use to cover their sinful heart.
Here's a good one. Why did God create the universe so vast? And if you could, do you have an analogy to help us get our minds around how vast the universe really is? And maybe a related question, if you went out to that furthest object, 13.8 billion years or light years away, could you go any further? Is there an edge to the universe?
I can answer some of those. Well, actually, I don't know why God created the universe as big as it is. I can only speculate, but one reason might be, well, we know the heavens declare the glory of God. That's something the Bible tells us. We know that's part of the reason. It might be to induce a little bit of humility in us, and I don't know about you, but it works for me. When I see the universe, and I think, wow, God is pretty awesome. It produces a very healthy fear of God in me, and we should have a healthy. We love God, but we should have a healthy respect for Him as well. The person who created 100 billion stars spoke them into existence, and that's just our galaxy. And He spoke into existence 100 billion galaxies. And it refers to it with this little phrase, He made the stars also. Like as it was just so easy for that. That is a person I do not want to cross. That is a person I want to make sure I'm on good terms with, okay? And of course, by God's grace, I am. He's opened my eyes to see that. But God did make an enormous universe. It glorifies Him. It should produce humility in us. Can I give you examples of how big the universe is? It's tough to do that because it's so big, nothing really suffices. When I was at the University of Colorado, they actually have a scale solar system on campus. And the sun is right outside Fisk Planetarium right there. And the sun it's about this big. It's on a pedestal, and you have the sun right there. And then the next, you go a few feet away, and then there's Mercury. And you look at Mercury, and it's tiny, 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 tiny. And you go a little further away, and then Venus, and then Earth, and Earth's about the size of a BB at that scale. And you're looking back at the sun, you're thinking, okay, yeah. And then you go out to Mars, and then you have to cross the street there, and you go to when you get to Jupiter, you're pretty far away. You can still see the sun there. By the time you get to Pluto, you're on the other side of the campus. It's that big, and because they just get bigger as you go out. And then the really fascinating fact is when you consider at that scale, where would the next star be? It turns out it would be on the North Pole of Earth. Okay, if the solar system is the size in radius of the University of Colorado, the next nearest star would be on the North Pole. That's the next nearest star, the Alpha Centauri star system, or Proxima Centauri. That's one, and that's the next nearest star. And our galaxy is made up of 100 billion stars. So that just gives you, it just starts to give you a little piece of it. If you really want to see it in action, the planetarium show I did, Created Cosmos, and of course you no longer have opportunity to buy it, but you already bought it, hopefully already. The Created Cosmos actually zooms in from the edge of the known universe all the way in to Earth, and it gives you kind of a feel for how big things are. What happens when you go out to the last galaxy that we can see? and go past it. Nobody knows, and that's something that's known to God alone. Is space empty beyond that? There probably is space. My guess would be there's space beyond that, but there may not be galaxies beyond that. It might be empty beyond that distance. One of the purposes of the lights in the sky is to give light on the earth, and so it seems to me God probably wouldn't make galaxies that don't fulfill that purpose. If they're so far away they never give light on the earth, then they probably don't exist. So the number of galaxies might be finite in the universe, perhaps, but we don't really know.
Wow. We're going to have to make this the last question since we're a little bit over time here. I've heard that the Earth occupies a unique place in the solar system, and that this solar system occupies a unique place in the Milky Way galaxy, and the Milky Way galaxy occupies a unique place in the universe. Can you tell us more about this preferred place?
Well, of course, that's exactly what we'd expect on the basis of biblical creation. God formed the earth to be inhabited, the Bible says in Isaiah 45:18. So all the qualifications that are necessary for life are right here. Yes, we are at the right distance from the sun to receive the right amount of heat and light. You push the earth more than about 5% closer, and we burn up. You push us more than about 30%. There's a little bit of a range. You push us more than 30% farther away, and we freeze to death. So we are in that right range. The sun itself is designed for the earth. Most stars that are kind of like the sun give off super flares, which are very, very massive outbursts of energy, and that would be very dangerous to life on Earth. But the sun doesn't do that. The sun is unusually stable as far as stars go. So it's the right kind of star. You don't even think about it, but there's different types of stars out there, and the sun is the right kind. It's exactly the right kind that we need in terms of its temperature. It's a yellow or white star. Red stars tend to be cooler than that. If we orbited a red star, you'd have to put us closer to it to get the right amount of heat, but then it doesn't produce as much light, so things would not be as vibrant, and we'd probably be tidally locked, which means we wouldn't have day and night. If you put us around a blue star, which gives off more light, you'd have to put us at a greater distance, and that would produce a lot more ultraviolet radiation, which is destructive. It causes, not only does it give you a nice tan, but it can cause cancer, skin cancer, and things like that. If you have too much ultraviolet light, it destroys life. So yeah, we're the right distance from the sun. The sun's the right type of star. We're at the right distance from out in our galaxy. We're at a distance a little ways out where we're not in the core where there's all kinds of other stars that would be nearby and maybe dangerous. We're not in the middle of a globular star cluster where we couldn't see the rest of the universe beyond. We're at a right distance not only for life, but also to be able to observe the rest of the universe. If you were right in the core of the galaxy, you might never know about other galaxies because there's so many stars there, they would prevent your view from the universe outside. And so we're in a position not only to live, but also to be able to do science, which is kind of interesting. And that makes sense because God created us to be inquisitive beings and to search out the universe. And again, He's planted these Easter eggs all throughout the universe. And I think He enjoys it when we find these things and we discover some new truth and say, well, isn't God amazing? His mind is certainly great.
Thank you very much. Let's give Dr. Lisle a hand. We're so thankful for you to share your expertise with us, and especially how you take this science and you point us to the Creator. As the psalmist says, the heavens declare the glory of God. And we certainly have seen a lot of God tonight.
Great.
Thank you very much.
My pleasure.
Thank you.
Thank you.
Why don't I close this in a word of prayer? Let's stand together and let's be dismissed together. Father, we thank you for what a truly blessed opportunity has been just to sit here, to sit back in our chairs and to consider your glory and your majesty on display in these features of our solar system and of the universe, and how truly it points us to you as an infinitely glorious and majestic and artistic designer. And we just thank you for the opportunity to consider these things tonight. I pray that they will have the appropriate impact to humble us, certainly, but also to cause us to stand in awe of you as our Creator, and to think that you, this infinite Creator, sent your Son to be the Savior of the world, that you demonstrated such love for us even while we were yet in sin. We thank you for the gift of Christ, the gift of salvation. We ask your mercies as we leave this place, that you'd give us safety as we return home. And for our speaker, Dr. Lisle, we thank you for what you've done in his heart and his mind, the gifts, the prodigious gifts you've given him. And we would just pray a special blessing on his science, on his ministry, on his life. And so thank you again for this time we shared tonight in Jesus' name. And all God's people said, Amen. Thank you. Wonderful, wonderful. Very, very good.